Welcome to our lesson on Chapter 6.1, starting on trigonometric identities. Today we're going to look at our reciprocal identities, which we already know, and our quotient identities as well, which we already know. And we're also going to look at what are called the Pythagorean identities, and we'll see how we can use our trig identities to simplify and rewrite trigonometric expressions, and we'll look at what are called some non-permissible values. So given the identities that we already have, the one that maybe we haven't used as much yet would be our second definition for cotangent. So putting cotangent in terms of sine and cosine. And this is going to be really helpful for us as we work our way through Chapter 6. When it comes to simplifying trigonometric expressions, what we always do as our sort of first step is to rewrite everything in terms of sines and cosines. The reason we write things in terms of sine and cos is because every other trig ratio we know, either using our reciprocal identities or using the fact that tan is sine over cosine, they can all be written in terms of sine over cos. And so there's a lot of simplification that happens in this unit, and that's our first step. So I have for us, I have a right angle triangle here, just taken from any point basically on the unit circle. So we have a hypotenuse of 1. Our horizontal side is the cosine of whatever angle x is, and our vertical side is the sine of whatever angle x is. And so we're going to start by making some new identities. Now, I kind of already gave away what we're going to do to start when I said that we're going to look at what are called the Pythagorean identities. So we know that Pythagorean theorem is a squared plus b squared equals c squared. And so I can substitute my side lengths of this triangle into Pythagorean theorem. Now, we recall that when we square sine or cosine, we move that square in on the function itself, but cos squared of x is cosine of x times cosine of x. This is our first Pythagorean identity. So this is our cos squared plus sine squared equals 1. We've probably used this already in some of the questions we saw in Chapter 4 as we were working our way through and finding like those questions where if we had an x, we had we knew what the cosine of x was 0.32. We wanted to know what the exact value for the sine of x. We would use Pythagorean theorem to work our way through and solve it. From this Pythagorean identity, we're going to come up with 2 new identities. And the first thing that we're going to do to come up with our first one is I'm going to divide all of the terms by cosine squared of x. And so if I divide both the left and right side of the equation, of course, I have to do that to keep my equality. And I'm going to go through and I'm going to actually write out explicitly what we're doing for this one so I can see that I am dividing, we're dividing by cosine of x. There we go. So we have our first term, cos squared divided by cos squared. Of course, it's going to give us 1. The second term, if we jump back up here for a second, we know that sine over cos is tan. So that's going to give me a tan squared of x. And then if we remember our reciprocal identities, I have cosine on the bottom. So 1 over cos of x is secant. And so 1 over cos squared of x is going to give us secant squared of x. And that is our second of our Pythagorean identities. So just by simple division, I've taken that first identity that was cos squared plus sine squared equals 1, dividing all the terms by cos squared, and I've come up with another identity that is 1 plus tan squared x equals secant squared x. Sometimes you'll see this rewritten if you move the tan over to the other side, so you might see it as 1 equals secant squared minus tan squared. As we work our way through this chapter, we tend to get rather lazy and talk about the ratio without the argument. Right? So when I say secant, I really mean in terms of this expression, I mean secant of x. So we have to remember that the argument's there, because if I just have a sign, that doesn't do anything, right? The sign has to act on something. Sign is a function, so it has to do something to some argument. So just because we don't say what the argument is all the time doesn't mean that it doesn't exist. What I'm going to try now, and I'm going to guess that some of you have already figured this out or had a pretty good guess at this is what we were going to do, is I'm going to see what I get if I divide by sine squared this time. So again, we'll write everything out. So I've got cos squared divided by sine squared plus sine squared divided by sine squared. That, of course, is going to cancel. 1 over sine squared. Okay, so jump back up here again, just in case we don't remember it. Cos over sine is cotangent. So cos squared over sine squared is going to give me cotangent squared of x plus 1. 1 over sine is cosecant. So 1 over sine squared is cosecant squared. And this is our third of our Pythagorean identities. So again, same idea. I do a little bit of division, simplify things, use my reciprocal identities, use my quotient identities, and I come up with a new identity that I can use. So it's probably a good time to sort of pause for a moment and take a look at all of the identities that we have. And I'm actually going to jump over to your formula sheet, and you can see that we have all those identities we were just looking at. So we have our textbook calls those first two identities our quotient identities, and then we had our reciprocal identities, and we've also added in for our reciprocal identities how to isolate for sine, cos, or tan in those reciprocal identities. So we can have sine as 1 over cosecant, and cosine is 1 over secant, and tan is 1 over cotangent. And then you can see the 3 Pythagorean identities that we came up with. So what I was about to say was, this is a good time to pause to figure out what we are doing with identities. And we use identities for a couple of things. By using identities, we can simplify complicated equations or expressions into simpler equations or expressions. So it makes it maybe a little easier to understand what the behavior is going to be, or maybe even just simply calculate things. We also will be able to use some of the identities that we see over on the right side of the screen. So these sum and difference and double angle formulas, we'll be able to use these identities to help us find exact values for angles that aren't on the unit circle. We also, in chapter 6, get our first real sort of look at actual mathematical proofs and seeing what we mean by a proof and how we can prove that identities are actually true or not. So it's usually a more complicated identity, and then we use the identities that we have to be able to rearrange those identities and algebraically show that they happen to be true. So there's a lot of subbing in, there's a lot of algebra, there's a lot of there's going to be some changing of denominators, changing the way things look. Multiplying by 1 is one of the tricks we use a lot, but when we multiply by 1, that 1 could look like all kinds of different things, as long as whatever I multiply by has the same numerator and denominator, and we saw a little bit of this earlier on as well. The next example that we're going to look at, we have some expression. We want to simplify this expression, and one of the things that we're always going to do when we simplify expressions is look for what are called the non-permissible values, and I will often refer to these as NPVs. So let's actually start there first. So what do we mean by a non-permissible value? Well, we mean a place where I would have an undefined value for the expression. And that would be where cosecant of x is equal to 0 or cosine of x is equal to 0. Now that leads me to 2 separate equations, doesn't it? So it leads me to either cosecant is equal to 0 or cosine of x is equal to 0. Let's start with our cosine first, just because that's the easier one to look at. If I draw myself a quick little unit circle, I can, oops, that's a wrong spot, sorry. I can see that I get two places where the x coordinates are going to be equal to 0. So x is going to be equal to, now instead of doing pi over 2 and 3 pi over 2 and using my k notation to show all of those possible values, because those points occur half a period away from each other, what I can do in terms of giving my expression is saying that that will repeat every half a period. So every pi k, and then of course k is contained in the integers. Okay, what about our other one? Well, we know that cosecant is 1 over sine. Now, normally what we would do if we wanted to solve this, we'd multiply both sides by sine of x, right? We're going to get that sine of x by itself so we can figure out where this expression would be true. But we run into a big problem because sine of x divided by sine of x, right? The reason I multiplied by sine of x, I'm left with 1 on the left-hand side, and 0 times sine of x is equal to sine of x. And the question is, when is that true? Well, that's never true. So maybe what we should look at then is there another way to look at look at what's happening here? So if I take that expression and I take the reciprocal of both sides, so I just rearrange it, so I get sine x over 1 equals, well, 1 over 0. This might be maybe an easier way to understand what's happening, right? So this is sort of saying, when is sine of x undefined? Well, if I just look at a really quick graph of sine of x, I know that continues forever, and there's no place where it is undefined. So there is that that condition for the non-permissible value of where cosecant of x equals 0, it never happens. Right? So we haven't really looked at functions of cosecant of x, and maybe we'll take some time and take a look at that later. But what I'm getting out of this is that there are no non-permissible values for cosecant of x equals 0, right? There are no values of x where we would run into trouble. So the only non-permissible values that I have means that when I simplify this expression, x cannot be equal to pi over 2, because if x is equal to pi over 2, when I simplify this expression, the expression would be undefined, because that cos of x, right, that cos of x in the denominator would cause the expression to be undefined. All right, so now let's simplify the expression. And when we say simplify the expression, what we mean is write, well, let's say write in terms of sine and cos, then simplify. There will be occasions where maybe we can use some of our other identities to simplify first, then write in sines and coses, or maybe something will cancel and then I write in sines and coses. But at some point in almost every identity we look at, or every simplification process we look at, we're going to rewrite in terms of sines and cosines. Okay, so cotangent is cos of x over sine of x. Cosecant is 1 over sine of x. And cosine, well, is just cosine. Okay, so I'm going to stack things. Here is a fraction divided by a fraction. Some of you might see simpler or faster ways to simplify that, and that's perfectly okay. I'm just going to make sure we can take care of anything that we might see. We, of course, know that when we divide by a fraction, we multiply by the reciprocal. So I'll take the reciprocal of that fraction in the denominator. And we probably see what some of you have already seen, that everything cancels out, right? Cos divided by cos gives me 1, sine divided by sine gives me 1. And so that expression is equal to 1. So for all values of x, cotangent of x divided by cosecant x, cos of x, is going to be equal for 1 as long as x is not equal to pi over 2 plus pi k. All right, if x was equal to pi over 2, or any multiple of pi above or below that, or if I add any multiple of pi from that, then that expression becomes undefined, because in the denominator I would have a 0, right? The cosine of pi over 2 would give me a 0, and then that expression would be undefined because I'd be dividing by 0. All right, so that example sort of combines everything that we're going to look at in this chapter. A little bit of simplification, looking for some non-permissible values. There's a Delta math assignment that goes along with this, so make sure you get that completed. And if you have any questions, just make sure you let me know in our next class.